All right, 4.5, exponential growth and decay continued. So the half-life of a radioactive element, unobtainium-37, is 20 seconds. If 80 grams of unobtainium-37s are initially present, how many grams are present after 20 seconds, 40 seconds, 60 seconds, 80 seconds, and 100 seconds? So I'm going to do the first one, and then we can kind of extrapolate from that what it's going to be for the other ones. Okay, so the first general equation is the amount is equal to the initial amount multiplied by e to the kt. So let's look at what the variables we have here. So let's see. So the question is, how much are we going to have? And this is a half-life, so we actually have to find this constant first. So our initial amount multiplied by e kt. Now, we don't know what the k is, but we do know that it's being multiplied by a t of 20 seconds. Okay. The variable we don't know initially is this k, because they didn't give it to us. They didn't give us an equation where it defined this k for us, this constant. See, in the next equation, see this right here, this is what we are missing. We're missing that constant of growth or decay. Okay, so we have to solve for that. Okay, so first I'm going to divide both sides by uppercase A. I'm going to divide this by uppercase A. And those go away. And we end up with 1/2 is equal to e to the k times 20, or just 20k. Okay, so next we're going to take a natural log of both sides, so we can get that variable k out of that numerator. Okay, so we end up with a natural log of 1/2 is equal to the natural log of e to the 20k. So now you're going to take this 20k and pull it to the front. And since natural log of e just goes to a 1, it just goes away. So you end up with a natural log of 1/2 equals 20k. And how do we undo the multiplication of k by 20? We divide by 20. Whatever we do to one side, we do to the other. These cancel out, leaving me k is equal to the natural log of 1/2 over 20. Okay, so the approximate amount of that is something like k is equal to negative 0.034657359. Okay, so now I'm going to go back to the original equation. A is equal to A initial e to the negative 0.034657359, and we put the t on. And the initial amount is 80, so I plug it in there. And now this is just a number, so we just plug this into our calculator and it should spit out the correct amount. So what happens is after you plug in there, it's very close to 40. So it's approximately half, which makes sense. If the half-life is 20 seconds and we start off with 80, after 20 seconds we should have half of it. Now, based upon this, it just should half every 20 seconds. So, right? So the amount when t is 40, so you have 2 half-lives, it should go down from 80 to 40 to 20, right? And then if the t was 60, it got halved again, so now the a should be 10. And then if the t is equal to 80, it should get halved again. So it should be down to 5. And if you have 5 again, you get 2.5 at time of 100, right? And that should make sense, right? This has been halved twice, 3 times, 4 times, 5 times. So it's 1/36, or 1/32 as much as it was previously. All right, so we're moving on to the next problem. Prehistoric cave paintings were discovered in a cave in France. The paint contained 4% of the original carbon-14. Use the exponential decay model for carbon-14. A is equal to a initial e multiplied or to the negative 0.000121 t power to estimate the age of the paintings. All right, cool. Now, first of all, if a is equal to 4%, that means it's equal to 0.04 of the original, right? So we could simply rewrite this equation of a is equal to a initial e to the negative 0.000121 t, except this, instead of being an entire part, is going to be a 4%, or 0.04 of the original. Now, next step, you're simply going to divide both sides by a initial. So it goes away, and that goes away. So it leaves you 0.04 is equal to e negative 0.000121 t. Now I want to get this exponent down to the front, so I'm going to take a natural log of it, and whatever I do to one side I do to the other. It gives me the natural log of 0.04 is equal to, and I'll keep the natural log here, of e to the negative 0.000121 t, except now I'm going to pull this entire exponent down to the front. So I end up with 0.000121 t. Okay, and then the natural log of e just goes to 1. I know that looks messy. Let me clarify. So again, natural log of 0.04 is equal to 0.000121 t, and the natural log just went away. Okay, so now at this point I want to solve for t. So I undo the multiplication of t by 0.000121 by dividing by 0.0000121, and whatever I do to one side, I do to the other. So the coefficient of the t cancels out on the right side, leaving me t. So I know that t is equal to the natural log of 0.04 divided by 0.000121. So we have to go back and make sure we put this negative in here, that negative exponent throughout the process. Right there, right there, right there, so they can see that. And that gives me t is equal to 26,602. That's close enough. It has a whole bunch of decimals, but that's good enough. Okay, so let's try the next one. So we say complete the table shown to the right for the half-life of a certain radioactive substance. So it has a half-life of 1,398 years and the decay rate of K. Okay, so this is going to be very similar to a previous problem we did over here where we solve for K. So we're going to have to solve for this K as well. Except instead of just using 20 for 20 seconds here next to the K, now it's going to have 1,390. Okay, so let's go back to the base equation, which is something like A is equal to A initial e to the kt. Alright, so now we know that the half-life, so it's half of the original, is equal to the original, right, e to the k. We don't know what k is, but t, we know t is 1,398. Alright, so now we need to solve this. Now first I'm going to divide both sides by the initial amount. So the a with the subscript zeros go away, and that leaves me 1/2 is equal to e to the k times 1,398. Right? Now at this point I want to get that k down, that k in the exponent down, so I'm going to take the natural log of it, and that allows me to pull it down to the front. Now whatever I do to one side I do to the other, so I take a natural log of the other side. Now at this point I end up with the natural log of 1/2 is equal to 1,398k natural log of e, and natural log of e just goes to 1. So I end up with a natural log of 1/2 equals 1,398k. Then if I want to solve for k, I simply divide both sides by 1,398. So the 1,398 cancels out on the right side, leaving me natural log of 1/2 over 1,398. So again, K, the exact answer is, it's the natural log of 1/2 over 1,398. So we plug this in the calculator and we should get approximately negative 0.000481343, and it just keeps on going on and on like that. Okay, so that's our approximate K value. So depending on how many decimals they ask for in your answer, in the answer box, you're going to put however many decimal places they want you to. And you're going to round appropriately where necessary. And that's it.